Hello guys, welcome to Lim Gao Teck's YouTube channel. Here is numerical integration part 2. We will go through composite trapezoidal method today. Okay, so here is a composite trapezoidal method where we divide the interval A to B to n segments, or we can say n sub-intervals. And in these sub-intervals, there's important points x1, x2 to xn plus 1. And then the first point is A, last point is B. So delta x is given by B minus A over n, and delta x is the distance between each segment, the length of each segment, as you can see here. This example is a example for n equals to 4. So you can see there's 4 trapezoid here. Okay, so this delta x can be given by this. Okay, so yesterday we used this trapezoid to estimate the area, right? So what is meant by composite trapezoidal method? Composite trapezoidal method is basically we use more than one n to estimate the value with equal segments. Okay, so when n is increased, the delta x is obviously decreased, so the difference with actual area decrease and the accuracy increase. So for this one, I will explain it in the next page. Okay, so as you can see here, this is the n equals to 1 where we did yesterday, and n equals to 2, 3, 4. Okay, so you can see that when the n increase, right, the length of a delta x decrease. So what happens when the delta x decrease? You can see that the difference between the real area under curve decrease. The shape of a graph looks more like the actual one. Okay, so the efficiency, the accuracy increase. Okay, so how can we get the estimate area under curve using this method? So you can see that there's n segments here, so there's n trapezoid here. Okay, so by plugging in the formula that we learned yesterday, what is the area of a trapezoid? Half times this side times with the summation of this plus this, right? So we did this to every segment. So basically you times 1 over 2 with delta x and with the value, the height of this plus this. Okay, so for the second one is this plus this. So you can see the whole term is here, and then we factorize out the delta x over 2 since it's a common term here. Okay, so for here you can sum it up. Okay, so you got this, and then you will find that there is a pattern here. So 1, 2, 2, 3, 3, 4, and then 2, n minus 1, n plus 1. So you can sum these terms up. In terms in between, you can find that the frequency is 2, so you got this. Okay, so except for the first and last term, the in between terms got 2. Okay, so your area as approximate area is given by this formula. It is important to know how to derive this, as you won't forget it. Okay, so let's do an easy example. We use the example that we did yesterday in the last video. Okay, with the same limit, but this time we use n equals to 2. We have 2 segments. Okay, so first we calculate the delta x, where you got the b and a, and then you know that n is 2, so you got delta x is 1 over 2. So you got the important points 1, 1.5 and 2. So now you just plug in the formula, and then for this one, when n is 1, you just plug it here, here, and here. So this is 1.5, you just plug it here, here, and here. This is 2, just plug it in and then press the calculator, you will got 9.35. So to say that the accuracy increased, right, now we need to implement a concept called percentage of error. So percentage of error is actually a true value minus approximate value divided by real value times with 100%. So you can see that this is the value we calculated yesterday with n equals to 1 and this is n equals to 2. So you'll find that n equals to 2 has lesser percentage of error, therefore more accurate. So thank you for watching this video. If you would like to see more math and engineering mathematics video in the future, do subscribe. See you all next time.